Okay, so this is the last lesson out of torque. Looking at a very specific kind of problem, ladder problems. And the reason ladder problems are so interesting is because of what happens at either end of the ladder. And so we'll see here what that's all going on here. So in this first example, we're going to get right into it just by looking at the forces that are acting here. So, right, the ladders are generally uniform. So we can consider FG acting at the center of the ladder. You climb ladders, and so your FG, part of what makes these things so interesting is that your force of gravity is going to slide along the ladder wherever you are at any particular time, which is going to increase or decrease your torque depending on where we put the pivot, and makes it really quite interesting. One of the keys here is that we're assuming that the vertical wall of the ladder is frictionless, which makes our life in this problem so much easier. That might not always be the case. Because the wall is frictionless, there is no force up or down here, but the ladder we know is leaning against the wall, so there has to be a normal force acting off the wall on that ladder. Likewise, there's got to be a normal force acting here. We're told that the wall is frictionless, but we don't necessarily have to assume that the floor is frictionless. I'll put it in here explicitly. Let's just assume that there is some mu value. We don't know what it is, but there's a mu. So then which way would the force of friction act? If there were no friction, what would happen here? Well, the ladder would just slam to the ground. And so the bottom of this ladder wants to move this way, so my force of friction is going to have to be in. On the simple ladder problem, these are the forces that we've got here. Obviously, things could change. We could put multiple things at different points on the ladder. We could add friction to the wall. But in general, this is the way the ladder problems are going to look. So let's take a look here and see if we can find the coefficient of friction for this particular problem. So we're going to use force components. We're going to use force components for all of this. I'm not going to use distance components for any of this. We didn't discuss the proper place for the pivot, but that's going to be a question-by-question basis. In general, though, the best place for you to put the pivot is going to be right here. Because in general, we don't consider these two forces to be really involved in the whole torquing of the ladder, the rotating of the ladder. And so putting the pivot there eliminates the weirdness of these two forces causing a rotation. So here we go. We've got some forces acting here. We got a force from the wall going straight up that way. I'll call that F wall. I called it Fn before, but I'll call it F wall now. I've got an Fn from the floor. I've got an Fg acting from the ladder, and I'm going to have a force of friction this way. We want to know what that mu value is. So force of friction is equal to mu Fn, but we don't know what the force of friction is, we don't know what Fn is, and so we have to use the fact that this thing is in static equilibrium to solve this. So we got static EQ, so that tells us three things. It tells us that my torques clockwise are going to equal my torques counterclockwise, my forces left equal my forces right, and my forces up equal forces down. So we can set all of these things up right away. Let's start with up equals down. If up equals down, well then this is going to be easy. There's only one force acting up, that's Fn from the ground. There's only one force acting down, that's Fg. We know the mass of the ladder is 10 kilos, so Fn is going to equal 9.8 times 10 equals 98 newtons. Love it. A little bit so we can see everything. Sorry. If my forces left equals my forces right, that means my forces acting to the left, my F wall, is going to equal my force of friction, and I don't know what either of those are right now, which is great. And now we're going to deal with the torques. For a lot of this, I'm going to use this expression here. Torque is equal to Fr sine theta, just because it's going to make, I'm not going to have to draw in all of my perpendicular components. I don't particularly want to draw in all my perpendicular components. This is just going to make my life easier. So we can see here that this angle here is going to be 30 degrees, and this angle here is going to be 60 degrees. This is going to alternate interior angles. If that's 60, then this is 60, because that force is is parallel to the ground. And if this is 60, that's got to be 30, because if we meet, this is guy goes going left and right, this guy's going up and down, so that's going to meet at a 90. So it's going to give us a 30, 60, 90 triangle. So we can use our torques here. My clockwise torques, if this is the location of my pivot, and this is the best place to put it, my clockwise torque is going to be given to me by my force of gravity here. So I'm going to have Fg times R sub g is going to equal, times sine of 30 is going to equal my counterclockwise torques. There's only one. If that's my pivot, only one of these is going to kick the ladder back out, and that's the force from the wall. So we're going to call that F wall, R wall, and that's going to be sine 60. Fg we know. Fg is 98 newtons. So we're going to get 98 times, we're told this is a 5 meter ladder, so that's a 2.5 meters from the pivot to the middle. So 98 times 2.5 times sine of 30 equals force from the wall. Our wall is the length of the ladder, so that's just going to be 5 sine 60. If you solve this, you can see here the only thing we're missing is F wall, and so we're going to get that the force from the wall is going to be 98 times 2.5 sine 30 divided by 5 divided by sine 60. So I get the force from the wall, so I punched it into my calculator, is going to be 28.29 newtons. Well, that's great, because we can see here, I'm just going to draw a line here to differentiate some of these sections, that F wall gives us the force of friction. So the 28.29 here is going to equal my force of friction, and then to find my coefficient of friction, I can just plug in what I know for, this should be Fn, what I know for Fn and Ff, and so I'm going to get that my force of friction equals mu Fn, my force of friction is 28.29 equals mu times 98, so I'm going to get a mu value of 20.29 divided by 98. 28.29 divided by 98 is 0.289 if I round it to 3 decimal places. And there we go. That is the coefficient of friction. Let's look at another question, very similarly, except now you're on the ladder. We're not going to use distance components here. We are just going to use the regular old force components the way we've been doing it now. There. So again, we got a 5 meter ladder with a mass of 10 kilos. It acts on a surface. Now, we're given the coefficient of friction, the maximum static coefficient of friction of 1.2 at an elevation angle of 60 degrees. So there's my 60 degrees right there. If a 55 kilogram person is 4 meters from the top, we want to find the actual coefficient of friction. So how much, what's actually acting here? This is the maximum. This would give us the maximum possible friction, but we don't have to have the maximum possible friction. We could have a slightly smaller value for friction, and this means the ladder wouldn't move, wouldn't slide. Like you wouldn't have to worry about falling if you were standing there on the ladder. So let's put a free body diagram together. We've got Fg from the ladder. We've got Fg from the person. This is both going to be 30 degrees in here. We're going to have the force acting outwards from the wall. I'll call that F wall. It's important to put the angles in here, so that's going to be 60 degrees right there. And again, I'm going to be using my expression for the torque is going to be Fr sine theta. Just going to make everything easier as far as the drawings and stuff go. We have an Fn acting up, and my force of friction is acting in. So again, static equilibrium. Everything is balanced. This thing's not moving. So my force is up equals force is down. My force is left equals force is right. And you got to remember why we're doing this. The reason that we can assume that these things are true is because this thing is not moving. So let's go through and put everything in here. We know we can give some values to these things. The person weighs 55 kilos, I believe, and so that they're going to have a force of gravity of 539 newtons. The ladder weighs 10, so it's going to have a force of gravity of 98 newtons. It's important that there's no coefficient of friction on the wall, because then there would be an additional upward and downward force. But we don't have to deal with that. Ooh, that would be fun, though, because then it would, there'd be all sorts of crazy stuff that would happen there. It'd be great, but we're not using it. So what this tells us is that Fn, my only upward force, is going to equal my two Fg's added together. So Fn is going to equal, that should be 600 and I want to say 37 newtons. And then my left equals right is going to be same as before. My F from wall is going to equal my force of friction. And for the torques, again, the place to put the torque or the pivot for the torques is down here at the bottom, because then all we have to deal with are these three guys going on up here. These two forces wouldn't have torques because the distance that they're acting at the same place the pivot is. So for these two, my R would be 0, not giving me a torque. So that's why we place it there. We still have enough to do here, though. My clockwise torque is going to be these two FGs. So I'm going to get FG ladder times R ladder sine 30 plus FG person R person sine 30 is going to equal F wall R wall. We're running out of space here. Sine 60. So I'm going to slide down and over here a little bit and put some values in. I'm going to get 98. Our total ladder is 5 meters long, so 98 times 2.5 times sine 30 plus 539. The person we're told is 4 meters from the bottom. This is important because sometimes it'll say 2 meters from the top. But again, we always want the distance from the pivot. So 4 meters from the bottom means this is 4 meters. So 539 times 4 sine 30 is going to equal F wall times the distance here is 5 sine 60. So I'll let you solve for that value. You can punch in your calculator yourself, verify that my value is correct. I found that F wall is 277 newtons, which tells us that the force of friction is also 277 newtons. So mu is force of friction divided by Fn, because, I should actually start here, force of friction is mu Fn. So I divided by Fn, Ff over Fn is mu. So my force of friction of 277 divided by Fn of 637, I get a coefficient of friction of 0.43. What that means is because the coefficient of friction we found is much smaller than the maximum static coefficient of friction, this ladder will not fall. Cool. And that is actually the only example I'm going to do with you guys, or the last example rather, I'm going to do with you guys out of this, and I'll let you play with some of these. There's some other interesting examples if you wanted to try them. This one was an interesting one, the 12 kilogram step ladder, but it's set up like this. Basically, the only difference is we assume that there's a wall here, and then this becomes a problem that we can look at where there's actually a cable tied to the wall, and then this force pushes back here, so there'd be a force that way, and there'd be a tension force that way. Interesting question. Give it a shot if you'd like. But otherwise, we're going to go straight to these exercises here. I'm going to give you a couple of these to look at. This I'm going to treat this as kind of an overall review. So questions 1 to 4. Well, it's not an overall review, a small review. Questions 1 to 4 are ladder problems. Question 10 is a beam problem I want you to take a look at. Sorry. And then I think the last one I want you to look at is question number... Ooh, usually I assign 11. Yeah, let's do 11. 11 is good. And that's just a general torque question. Yeah, question number 11. That's the last one let me look at. So this is the last lesson. I've also posted the review that goes along with this chapter. The questions from these lessons are going to be, so if today, if these videos were posted on Monday, these lessons are, the homework for them is due this coming Sunday. The chapter review is due the Wednesday after that. If you get it done by noon that Wednesday and post it, I will make sure that I take a look and grade your reviews that night. And then the quiz for torque is going to be next week Friday. So not this. So if today's the day, if I'm posting this on Monday, 5 days is Friday, but then a full week after that. So I guess 12 days from now is I guess when I want you to look at the quiz for torque. It'll be ready to go that day. As always, comments, questions, concerns, please feel free to email me.